Okay, good morning, everyone. So last time we have already talked about the basics related to the contamination and then the yield issues, and then we also talk about the what actually the factor will in the end influence our yield. And now we'll move on to some equation. In the end, we can help us. This equation can help us to have a certain yield calculation. And to try to derive the equation for yield, we first have to introduce some statistical basics. So today we will talk about the statistical basis for yield. And then the things we would like to introduce is actually something that you have been learned from the high school, but probably you haven't used for a while, but now it's going to be really useful for us, especially to consider for the yield, which we call as binomial distributions. So this binomial distribution can be physically described by, we can first to consider this, to understand the binomial distribution, we can first to consider the very typical case that we try to toss in combs. And we all know that when we toss the combs, there will be only the two outcomes, which is heads or tail. So that's actually the front side of cone or the back side of cone. So that's only the two possible outcomes if we try to toss one cone. So if the probability of getting a head in the one trial toss, so that means if we try to toss one cone once, and then the probability to get this a head for the first trial, what we call as a P, and then the probability of getting a tail, which is a Q. And therefore, we all know that no matter which outcome can be, in the end, that the overall probability must be equal to 100%. So which means that P plus Q in the end is always equal to 1. And then if we consider this is unbiased tossing, that means that there's no additional factor will influence the result. In the end, that if we try the many times as we have, in the end we always get the probability to get the head, and then the probability to get the tail is 50%, which is equal to the 1/2. So that's the starting point when we talk about the binomial distributions. So the same phenomenon holds for the once we consider we toss for the n coins, or we toss one coin for the n times. So we consider for the n tosses, where the probability of obtaining at least one head or at least one tail is equal to 1, which means still the P plus Q power of n still will be equal to 1 if we try to toss for the n times here. And then we can try to generalize this calculation which consider as a binomial distribution. The general form for the binomial distribution can be written as follows, where we have a P plus Q power of n is equal to the summation from the k to n, k equal to 1 from the first toss until the n tosses, and then which is n fact, which we have the n factorial divided by the k factorial times n minus k factorial and times the p power of k and times 1 minus p power of n minus k. So this is some equation that we should already learn from the high school. That's a general form for our binomial distribution. So this equation is exactly shown in the next page. This is a result where we extend to n coins, each flip once, or one coin flip n times. The probability that n heads will be obtained in n tosses is shown here. That's exactly the equation where we shown previously. So we can try the very simple calculation first. So in the simple example, if we consider 3 coins that toss once, so what is the probability of getting exactly 2 heads here? So if you try to count for if you toss 2 heads, and then there's overall can have 8 possible outcomes. So we have 3 coins, and then each coin only have the head and tail. So in the end, we should have 8 possible outcomes, which is all heads, or 2 heads, 1 tail, or this one. So these are the 8 possible outcomes here. And so therefore, the question is that what is probability of getting exactly the 2 heads here? So we, from this, because now we list all of the possibility here, and then the outcome for 2 heads, which is here. We have the 2 head here. We have the 2 heads here. We have the 2 heads here. So that means that the probability that for this question is 3/8. So basically this is a very simple experiment, so we can easily try to consider, we can easily list all of the possible outcomes, and then we can try to calculate the condition, the answer for each probability. And then also the answer also can be direct calculation from this above equation, which means we have a P is equal to the N. Now we have 3 coins, so the capital N means 3 factorial divided by 2 factorial and 1 factorial and times power over 2 and 1/2 power over 1, which still will be equal to 3/8. So this is just a quick illustration that this general equation in the end can also help us to calculate these simple experiments. So therefore, when we consider binomial distribution, it's physically described by tossing the coins that had 2 outcomes, and the general form is shown here. And now we will consider the Poisson approximations here. So we try to apply the Poisson approximation to this binomial distribution, and therefore we can rewrite this equation as a P of n at a given n and P is equal to 1 over n factorial exponential minus np. So that's a result that we apply from the a very simple approximations. So then what does all of this have to do with yield? Because now back to our question is that we want to extend this binomial distribution to help us to have an equation to calculate as a yield. So suppose now we have a number of events where we can consider that each defect is also as an event. So we have a number of defects occur randomly in a nearby non-overlapping domains, and these events are independent with each other. So these are the independent events in this specific area. So now we consider that we have the number of defects, and then each defect won't influence and won't overlap with each other. So now we can consider these defects are independent with each other, and therefore the probability of a chip containing the n defect can be given by this equation, which we shown in the previous slide. So in previous slide we have this Poisson approximation, and we use this Poisson approximation on this binomial distribution to help us to calculate the probability of a chip containing n defect here, and in here this is a 1. And therefore the probability of a chip containing 0 defect can be defined by this equation as well, which we put the n is equal to 0 here, because in the end we hope that our overall our chip that has no defect here. So if you put the n equal to 0, in the end will be equal to this one, and then we can have this y is equal to exponential minus alpha here. So if the defect density or number of defects per unit area is we consider as a d, so that's a defect density, then the alpha is equal to d times one specific area here. So now in the end we can get this very simple equation where y is equal to exponential minus dA. So this is an important equation express the probability of the chip having no defects. And then right now we first to consider this is a case that defect density is a constant. In general, we consider very simple case that we have the constant defect density, and then we can have this very simple yield equation where we consider there's no defects, that the probability of the chip having no defects here. So again, this is one example that no matter when we talk about semiconductor physics or we talk about lots of engineering question, especially in the semiconductor field, although in the beginning we might starting from a relatively complicated equation, but if you take some patience, in the end the equation is always looks very simple, just like here. So y is equal to exponential minus d times a. That's a way too simple equation, but that's already very useful for us. So now we consider another case that if we have the wafers with n dies, and what does mean the die? The die means that if you take into account the wafers here, so if you have the so now if you take into account that for the one wafer here, and then normally we will try to cut this whole wafer into small pieces, because normally we won't have the one chip that contains all wafers, so we will cut this with lots of small chips here. And therefore we consider that each small square as what we call the die. So now if we consider one wafer with n dies and with also the n defects that are randomly distributed in the wafer, then the probability of a given die having k defects can be also given by this simple Poisson distribution, which we have the equation showing here. The pk is equal to exponential minus m, and m power of k, and divided by k factorial here. Therefore, the probability of a die having 0 defect, that means this is a good die, is then given by putting the k is equal to 0. So now if you consider k is equal to 0, so again this equation will coming back to this one, which is P0 is equal to exponential minus m. And then if you also define the chip defect density D0 per die per unit area, then again we still can come up with the same equation which we consider, which we derive before here. So in general, the yield is highly correlated with area and also the defect density. So normally, because this is a exponential minus function, right? So we can expect that the area increase or the defect density increase in the end cause that we have the chip that has a lower yield here. Although of course, if we solve this equation, is also pretty common sense that with a large chip size, with a higher defect density, in the end we always have a low yield. But now still we have another solid proof coming from the more rigorous mathematic calculations here. So the strong exponential decrease in yield, which with increase in area and D, should be appreciated. So that means that we should be careful that the yield is exponential decay with area A and D. And as we shown in the previous slide, y is equal to exponential minus dA here. So therefore, if you consider the die size, original we have the 1 centimeter square, and in this die size the yield is equal to exponential minus d. But now if we try to consider, we increase the die size, become 1.5 centimeter square, and therefore the yields now will be reduced as an exponential minus 1.5 e here. So this is a sentence described here as a consequence of enlarged die area from 1 to 1.5 centimeter square, that will yield, the yield will drop by factor equal to exponential of this one. So that's a huge difference, because in the end it's an exponential decay. So we increase 50% of our die size, but yield will, this will highly influence our yield. So the next one is that we are interested in the yield modeling. So in the previous case, we only consider as a defect density of the constant. So instead of being constant, in reality, we might have a different kind of a defect distribution. So the defect density here varies according to the function of the FD. That's again the density function here. So therefore we can re-put FD in the previous equation, but now if you consider the n equal to 0 and the yield is y, again integration from 0 to the infinite times the density function FD exponential minus dA d here. Because now we try to generalize that in the previous case we only consider the defect density as a constant, but in reality the defect density can be all kinds of a possibility here. So to capture the defect density, we introduce this density function, and therefore we can generalize the previous yield equation, become now which yield is dependent on the, again, defect density, area, but also the density function here. And this integral proposed by Murphy, which is now as a very important role in yield modeling. So let's just try to look at the several cases that you might start to get a sense that how we don't have to do this yield modeling. Might be in the future for your work, but just give you some ideas that how did the previous scientists, researcher have been done. For example, if you consider the constant D. So in the case with a constant D, and then we actually notice that the defect will be only happen at this location. So then the density function FD behaves like the delta function. So the FD is equal to 0 everywhere, but FD will be equal to this one at this particular locations here. So now if we put again this information back to the previous integral, then we will also get the same conclusion that the y is equal to exponential minus d0a. So everything is consistent. If you try to use the previous integral and we consider the constant defect density, then we still got this exponential minus d0a. But of course, it's getting complicated if we consider the triangular. Why we use a triangular? Because sometimes triangular can be the approximation. Triangle can be the approximation to a Gaussian distribution here. So this is a second case. And again, if we consider this distribution function, in the end, the integral can lead us to have the equation as shown here. So similarly, if we consider exponential distribution as here, so then we got this result as a yield. So in here, we won't derive one by one, just let you know that if we take into account the different defect distribution from the constant, triangular, exponential, Gaussian, or gamma, and we can always to do the yield calculation based on this defect distribution. To simplify this estimation, some people also made it as a graphic representation of this for the case with gamma and Gaussian. Gaussian and then gamma distribution as shown here. And with this one that we can estimate the yield versus a different D0A by using this graphic here. So now if you try to extend the understanding of this yield versus our real practical experience, then normally we can see some correlations here. So the yield generally declines in dies located at the edge. So this is one of the experimental results that this is a cheap yield versus the radius distance from center to the edge. And where is the edge? This is edge. So now we can see from center we have a high yield, but as long as we close to the edge, we always have the low yields here. As the number of process states for given product increase, yield, not surprising, is expected to drop. As well. So if we have a more process state, then we can expect that the yield will be dropped as well. So this is one of the example showing here. This is the number of the state. We have 100, 200, 300, 500, and then we can see that as we have a 500, and there is a very fast drop for the yield. So the yield projection using the following is sometimes considered as a little bit worst case here, because the defect because the defect in the end is preferred to congregate at a certain location. On the wafer. So in reality, we might see that the defect will always try to accumulate at some region. They will be really close by. They will congregate with each other in a certain location, and this is a case we call as a cluster here. So rather than distribution randomly. So therefore, normally we will see there's some unexpected defect-free area that can give us a high yield. So that's why because this equation is considered as randomly distributed, but in reality that we can see the defect will tend to be located in the nearby region, and then they congregate as a cluster, and then we will see there's some unexpected defect-free region that give us a higher yields. So when we talk about the yield and reliability, especially we have to define the difference between the yield and reliability. That's a pretty important concept. So in the yield modeling, the concept, we have one concept called the critical area. Arise as a mathematical quantity that describes the probability that a defect will result in the yield loss due to the complete open or short. So we have to figure out that what does mean this critical area here, and therefore with this critical area that will cause yield issues. So our yield can be written as a y0 exponential minus d a y here, and where this is our yield critical area. That's AY. And why we have to consider yield critical area? Because there is another term very similar, but that we only call as a reliability critical area here. That's we call the AR. So again, then our reliability is equal to R exponential minus D reliability critical area. But now you might wonder, what is the difference between the yield critical area and the reliability critical area? So we can use this schematic to illustrate the difference. For example, we can see in this interconnection line, some kind of the interconnection region is become thinner and thinner, but this interconnection line still functional, although the resistance can be increased. So that's the reliability issues. Right? So we might see the interconnection line might be thinner in somewhere due to some additional damage, but this interconnection line can still flow the current, but the resistance is increased. So therefore, this area we consider as a reliability critical area. But on the other hand, if we found out that as long as the reliability critical area is enlarged to the certain amount of area to reach to this level will in the end cause the yield issues. Because this is a completely open. So therefore, if once this completely open is happen, that means your current cannot flow from the top to the bottom anymore. Your current cannot flow because the interconnection line is completely open, and therefore this area is what we call as the yield critical areas. So now you can see that there's a difference between what does mean the yield and what does mean the reliability. Reliability is generally suggests that there is a performance degradation, but still the device or the interconnection line are still functional, can still operate, but we just lose some performance. But yield is generally considered as a completely broken, completely open, complete short, and then the interconnection lines or the device are not function anymore. So the these two critical area can be related to these K factors here, and also we can consider the equation as shown here as R is equal to Y exponential K, and that just depends on the what would be the K values here. So there's a certain correlation between R and Y. That's between the yield and also the reliability function. So this is a reliability functions, and this is a yield function. This is a yield function. So here we see some of the experimental testing result here. So this is, although this is coming from the very old textbooks, and the figure probably coming from the relative old literature, but just want to let you know that there's a certain correlation between the yield and reliability here with a certain correlation. And then in this case, the K is equal to 0.3, and then the correlation between the reliability is equal to yield power of 0.3. So also it will be interesting to know how to determine the AR, and then also if we want to determine the AR, normally is first to calculate A1, which is a critical yield reliability. And then in here we show that this is a general equation that we try to calculate the A1, the critical yield reliability, which is equal to A1 is equal to the integration of the 0 to the infinite times our probability that can cause the yield times the defect density function here. So P is a probability that defect size will cause a yield, and then the D is a defect density functions here. So here is some more illustration that just want to a little bit focus on the difference between the yield defect or reliability defect. So the yield defect is normally the defect that will completely cause the course completely opens. For example, if we have the interconnection line as shown here, and now we might have the defect which has a larger than our interconnection line here. So this kind of defect will cause the yield issues. If this kind of defect will cause a yield issue, that we classify as a yield defect. So it's a very simple concept, just to try to be more precise the difference between the yield and reliability. So yield is just a kind of the defect that will completely open the interconnection line. But on the other hand, as we already illustrated previously in the slide, that if we have another interconnection line here, and then we have the defects in this region, but this defect will be only cause the unresistant change, because the defect will occupy the certain interconnection line, and then in the end the current is decreased, the unresistance increase. So therefore we have the unresistance increase, and therefore we can consider this defect as a reliability defect. So as shown here, reliability defect cause near opens if the particle reduce the cross section of an area of the strip line below some arbitrary value. So in anyhow, what this means that this kind of defect will try to occupy the certain interconnection line, but that will not cause completely open, just a near open, but in the end this interconnection line is still functional, and thus we classify this as a reliability defects. So in the textbook, also in the past literature, people try to consider the cases that we have a different particle size here. So this is one example that this is considered that where reliability defects are assumed when the cross-section area is reduced below W/4. So that means if you have this interconnection line, but now we put the W/4 as a one criteria, as shown here. Reliability factor. When the reliability factor defined as a metal is remaining below W/4 here, and then the yield defect occurs when our defect size is larger than W here. Then we can try to consider the different particle size here. The different particle size, which sometimes this size will only influence the reliability function, but sometimes this defect size in the end will cause the yield function difference. So the PYX is a probability that defect size X will cause a yield defect, and PRX is a probability that defect size X will cause a reliability defect. So we can actually further try to define as a more clearly condition to differentiate between the reliability defect and then also yield defect, and then with each particle size we can have this PR and PY that can be obtained. So this is one of the examples that how in the past people do the modeling, try to take into account the different defect size in the end to understand the influence of yield and reliability. So this figure just another way to conclude this chapter, that in the end consider the yield and reliability. So when we consider reliability, as we already mentioned, that the reliability is when we define reliability, we have first take into account what is actually the operating stress, what will be the values, and what is the time during the stress here. And when we consider yield, we have to take into account what's the process issues, what is the materials issues, and what is the design issues. And then these yield and reliability can be connected with a common concern, which is defects. Because sometimes when we consider reliability, we do a certain stress, we see that there's some drift of our device characteristic, which is mainly due to there's a defect generation under the certain location. And this defect generation, when this defect is growing as larger as possible, then will cause the yield issues. On the other hand, also, when we do the process, when we use the materials that has a problem, when we have the poor design, that can also cause these defects issues. And this defect issue will also influence our stability or reliability of our device under the certain operations. So in the end, the defect can be the common connections and common concern, no matter we are looking from the reliability side or we are looking from the yield side. Okay, so there's some reference video you can look up. I think right now there's many reference videos that talk about the very basic related to yield and then binomial distribution. So in the end, that from this chapter, what we actually learn is that first, we have to understand that the defect is something that we cannot avoid in the semiconductor material, because no matter how good our device, how good the material, how good our process can be, we always will certainly introduce a certain defect. And this defect including, for example, point defect, dislocation, and this defect will highly influence our device performance. And also, from this chapter, we learned that the yield with the basic equation, yield is equal to exponential minus d times A. So that means the yield is highly depends on the defect density and then the die area. And then we can use a different way to support this understanding of this equation by using the statistical model. For example, we consider the binomial distribution. We take into account the Poisson approximation, and also there's one what we call the Murphy's integral. So in the end, we always get the same conclusion. And also, we have to be aware of that in most of the modeling, we consider the defect is randomly distributed. But in reality, the defect prefer clustering with each other. So that means that the lots of defect will be located, very localized in the one area, and you will surprisingly see that there's some area that has no defect, which is a defect-free area. And in the end, this will also impact on our yield outcomes compared to our ideas model. Ideal model is taken into account as a randomly distributed. And also, the yield and reliability, these are actually the issues that are connected with each other. And there's a concept we call the critical area. And therefore, also, what in the end for the product manufacturing in the end is try to improve the yield. And first we improve reliability, and then we improve the yield by consider the process control and also certain defect mitigation strategies. So we try to remove the defect as possible as we can. So if you look at the real production semiconductor tool, there's some company where they make the tool is for the defect inspection. So that means that the tool is only to look at the defect, to calculate the defect density. But this is information very crucial, because once we know where the defects are and how these defects coming from, and then we can understand how to, that can be the important clue for us how to reduce the defect density, in the end to increase the yield. Okay, so we finally will move to the certain very critical part for the reliability, especially in the when we talk about yield. We already introduced some basic concept for the statistical modeling. Although from the beginning of this class, I already illustrate that what we normally learn from semiconductor, from my own experience, that most of us will focus on the learning, understand what's the process from each of the process, that how to make the semiconductor device, the fabrication process, and then we will try to understand the semiconductor physics. But most of us will missing that there's a critical part about the mathematics. But this mathematics is not the one we learn from the semiconductor physics. The one we learn from semiconductor physics is the one we try to understand the device physics, try to understand the carrier transport, try to understand the quantum tunneling. That's why we also need the equation. But on the other hand, there's huge part of mathematics is mainly try to leverage the advantage of the statistical model to help us to estimate, to project the reliability and then also the yield. And then in the end also we can leverage this mathematics to understand the values here. So therefore this chapter is also very critical because of this chapter is something that you won't learn from any other general semiconductor textbook unless you are in the field of reliability. But my experience told me that in the field of reliability, in the most of literature, even in the loss of a reliability engineer, they know why, they know how to use this distribution, but probably they don't know why. What is the fundamental reason that why we can use this? So sometimes that you see the lots of literature, they just told you that they use this one to do a live fitting, but you probably will be puzzled why, how come this can be used. So this chapter will mainly describe the origins from the very beginning, that why we feel like this mathematics could be useful for us. So by the end of these lectures, you should able to able to explain the role of the statistical distribution. This term should not be pretty new to you. Some are very old because you probably already know what does mean the normal distribution, what does mean the exponential distribution. Of course, there's something new. For example, log normal and Weibull distribution. These are the distributions that normally you won't hear before, but now in the future you should pretty heard about this term, especially if you are working in the industry afterwards. So in here we will talk about the normal distribution, exponential distribution, the Weibull distribution, the log normal distribution, that the role of this distribution in modeling the device, value and reliability. And we also will talk about some key important parameters such as a value rate. So as we described in the beginning, that the overall goal is not only do the testing, but in the end we want to predict the testing. We want to know how long our product can be survived. If we want to know how long the product can be survived, for sure we need to know how fast the product will be failed, and therefore we need to try to find a way to estimate the failure rate. And also there's a term called the mean time to failure, MTTF, where we already mentioned, and also the survival function. And also in the case of the industry, we are pretty concerned about the statistical process control, that's SPC. And we also have this Six Sigma process control concept. We will also talk about this. And also we will also talk more about the difference between the series and then the parallel system, that in the end will influence our probability rules. And also there's some physical model in here. We try to correlate with our statistical model, and we will consider as arenas. And also there's a very important what we call the weakest link theory. So the weakest link theory is a fundamental reason why we can consider the Weibull distribution for so many semiconductor device, statistic distribution and the modeling. So it's definitely it's very crucial to understand what does mean the weakest link concept. Okay, so the first one is introduction, that This chapter will focus on the mathematical methods that employ in analyzing product quality and value data. Especially, it's very important to know that the reliability measurement reliability mathematics and analysis. In the end, our goal is to predict the fate of the product. So that means we want to understand the lifetime of the product. For example, here is we can give you the very simple example. For example, if we try to stress at one fixed voltage, like say 5 volt, and we found out that the degradation rate can be, for example, delta VTH shift, which is equal to 0.02 volt per hour. So that's the degradation rate. But if we take into account for the criteria for the semiconductor, in the end we hope our device can have the maximum VTH shift cannot be larger than 1 volt. If the delta VTH is larger than 1 volt, then we consider that our product is a fail. So with a degradation rate, with a criteria for the maximum threshold voltage we can have, and therefore we can do this very simple calculation to estimate the lifetime, which means this product can survive less than 50 hours. So that's the goal. We want to get this number. We want to understand what is the lifetime for our product. So that's the goal. So although this example is very simple because we use a constant degradation rate, and then criteria is also simple. So in the end, overall calculation is very simple. Of course, in reality, sometimes the degradation is not just constant here. It's getting more complicated. And criteria that will not only to take into account as a threshold voltage. Sometimes we have a unresistant, we have a lead current, we have the multiple criteria here. But this is just an example that how important of this value rate, and then this value rate can give us idea that to predict the lifetime. The fate of a product actually just means a lifetime here. So in order to predict reliability or the fate of product more extensive, normally we have to do lots of extensive, but also which is a very destructive testing. So we need to have the extensive time-dependent But also it's very important is the destructive testing. So what does it mean, the destructive? Destructive means that we have to test our device until the broken. And then once it's broken, we know the maximum lifetime or maximum condition that our device can sustain. So this, which contains the first one, time dependent. That's already we have been described in the beginning of this class that when we talk about reliability, it always is a time dependent issue. But another factor is that we have to test until the broken. We have to test until the device, until the failure. So for my personal understanding that the most interesting fun for doing a reliability study is that you have a lot of opportunity to try to destroy your device, because this is a purpose, this is needed, this is necessary. For most of if you are doing the performance related semiconductor study, you probably will put your device as like the golden baby. You try to protect, you don't want to destroy them because you only have the few of the device. But in the sense of reliability, we just want to destroy everything because of the limitation of our semiconductor device can be only understood if we see the value. If there's no value, there's nothing fun for us. We need to stress, we need to destroy it until that shows a value. Once we know the value, we can determine the time, we can determine the mechanism behind. So that's the most interesting part for being a reliability study. So therefore, we need to have this very extensive time-dependent destructive testing will be required to allow the value of a failure rate to be determined, because once the device is completely failed, finally we are able to extrapolate the failure rate. So that's the purpose. And these are extracted from other mathematical functions, for example, exponential. And log normal, and also in the end the Weibull distribution. This is extracted from these three are very important. Exponential is not surprising. I think overall in the many engineering problems, we always try to apply the exponential increase, exponential decay to do the modeling. So I think exponential is one of the most often used equation in the engineering field to do the lots of the modeling, to do the characteristic analysis. But the other tools, log normal and then Weibull distribution, are pretty unique here, because normally you won't heard this in the other field. But once you are in the semiconductor, being professional and being more practical towards the product development, you cannot skip the part related to the log normal and Weibull distribution. And we need to use this in the end to fit the value data. So that's very important. And then you might wonder, how do we use the distribution? Because as you from your understanding of distribution, try to just collect a number of the event and try to plot in certain distribution. But how do we use this distribution to fit the value data in the end to predict lifetime? So that's a key part for this chapter. And then before we go to very complicated distribution, because some distribution is really complicated, even the equation cannot be simply drawn by hand. Most of the equation in the log normal and Weibull, sometimes they need a certain software to help us. So we're starting from the very basic one, what we call the normal distribution function. This is just a basic introduction to remind everyone that how do we leverage the distribution to help us to analyze one thing. So a useful skill for engineering concerned with the product reliability is to be able to convert a large amount of data value data into a form that we are able to analyze. Because in the beginning, when we test 100 device, 1,000 device, in the end we collect a large amount of value data. When you in the industry, it's just not like in the university lab. In the university lab, normally you probably only test like 10, maybe 100 devices. That's already quite a huge burden for everyone. But in the real industry, they produce a product day and night. They have the 10,000 wafer per month. So in the end, we have a huge amount of data. When we have a huge amount of data, sometimes this data is kind of like the pretty in the messy form, which means that it's difficult to understand, it's difficult to analysis. You just have the bunch of the raw data, but we need to convert this messy data to the way that we are able to analyze. So here is an example how to analyze the fuse reliability. So what is fuse? This is a fuse. 灯丝. This is a fuse. So this is a table that has a value current measure. This is a table that has a value current measure for such a population of 100 fuses. So we have the 100 fuses result and test until the fail, and then we collect all of the result here. For example, the first one is broken at the 9.6 amp. The second one is broken at the 10.22 amp. The third one is broken at the 9.46. If you just quickly scan all this data, you probably will know that this value is all around 10 amp, right? Because all this value is broken, and when the current reaches a condition around 10 amp. But it's not exactly 10 amp. There's a spread, sometimes higher than 10 amp, sometimes lower than 10 amp. And how do we analyze this data? Because this is a messy data that we are not able to analyze. We only roughly know, yeah, there's a 10 amp. But why sometimes higher, sometimes lower? how do we convert this in the more useful analysis? That's why we need to have this statistical analysis. And also, this statistical analysis is not that complicated because it's also very straightforward. So, in reality, we always try to convert this data from the raw measurement data. This is raw measurement data, and we create the first distribution that we call the frequency distribution. So it is convenient to first to create a value frequency distribution. So that means we just try to look at this table and then come up with a certain range, and then we just collect to summarize. For example, in the range between 8.7 n and 8.9 n, we found that there are 2 fuses fail in this range, and in the next range 8.9 to 9.1, there's no any fuse fail in this range. And in next one 9.1 to 9.3, there are 7 fuse fail in this current range. So that's we call the frequency distribution. So the first homework we are doing, just try to classify with a different current range and try to calculate how many fuses are failed with this specific current range. And the next one, mention here, for this purpose, the range represented by minima and maxima current is arbitrarily subdivided into a number of cells. For example, we divide as 11 as a total current, 11 current range here, and the number of fuses destroyed in each current interval is noted in here. So that's the first step. And second step, we do this what we call the cumulative distribution. And this is also very simple. We actually just try to define as an upper current limitation and then calculate how many fuses fail below this current criteria. For example, in the case of 8.9, this is 8.9, so only 2 fuses are failed. So we just fill in this as a 2. And the next, if we move to the 9.1, because of 9.1, in this region, there's no additional fuses fail, so this still will be the 2. But in the case with 9.3, we have the 2 plus 0 plus 7, so we got this 9. Which means this plus this plus this will be equal to the 9. So that's what we call the cumulative distribution. But in the end, this will be reached to the 100 because we got the 100 total fuses. So in anyhow, the loss will reach to the 100 cumulative number, which means this is reached to the case of a 100%. And therefore, we start to have this cumulative percentage. With this range, we got to 2% fail. So that means that when you stress your fuses up to 8.9 amp, only 2% will fail. This will be 2%. This will be 9% till the end. So finally, we got a little bit more meaningful interpretation of all these data, because right now we understand that in which current criteria, how many percentage of our fields can be failed. If we only test up to 8.9, we only have a 2% fail. But if you test up to 9.9, like here, if you test up to 9.9, you got almost half of the fields fail because it's already 52%. So that's important information, because now we convert all the amount of data in the distribution way that we are able to analyze. So first of all, with this frequency distribution, we can already redraw the data as this histogram. So this is something that we should also learn from the high school. Histogram here. So this is a basic as a plotting from here to here, right? So we just try to, we have 8.8, so that's 2, 9, we have the 0, 9.8, which is around here, we got 22. So that's just a way to summarize of this frequency distribution. But the most importantly, it's not the frequency distribution. Actually, in the end, is this cumulative distribution. Because as we already say that just to mention here, it's common to plot failure data in the another way, which is cumulative distribution. So the number of failures that occur less than or equal to a given value is noted. What does mean? This means just as we consider this upper current criteria, how many fail below this criteria is summarized here, and then we can convert all of them as a percentage, as a 2%, 9%, in the end to the 100% here. Then we can start to plot this cumulative distribution in the y-axis, and also the upper current limit as x-axis. So we can create this, what we call the cumulative distribution function. Which is we call the CDF. And then from this graph, we can understand that, for example, in the case with a 9.8 amp, probably will be equal to here. Then we have around 50% of our fuse fail. So finally, This is important information because we can understand that with each current level, how many devices are failed, how many fuses are failed. So then, a cumulative distribution function CDF can be defined. So let's just look at some more example in this CDF here. So as shown me here, we have the CDF. We have this graph where the y-axis is the CDF, and then the x-axis as a current. So we have a 9 amp, 10 amp, 11 amp. So imagine that what would be the best case we want to have. If we want to have the best uniformity of our device, that means the best unity for our product. That means the product will be only all fail in the one phase current, and there's no spreading of this. So which means the best ideal case, which is there's no any fail until 10 amp, and all of our semiconductor device, all of our fuses are broken exactly at the 10 amp. And then beyond the 10 amp, this will become like this one. So, right, this is our best ideal case. This suggests that our product has a very good uniformity. Because all of the devices are broken exactly at the 10 amp. If we stress the device at the 9.8, 9.7, we don't have to worry about the failure because the device won't broken. On the other hand, what would be the worst case? The worst case can be there's a huge spreading of this current that can cause a failure. So some fuse already broken at a very low, for example, probably like the 9.5 amp, and slowly increase. And some of the fuses needed very high current beyond 11 amp. So this means that we have a very wide spreading of our current that can cause a failure. This suggests that our product has a very poor uniformity. So, in the end, the graph, the plot showing here, become very straightforward understanding. If we can have the device that can have this steep slope as possible as we can, that suggests that we have very good uniformity. But if we have this long tail towards the left and towards the right, that means we have a poor uniformity. So that's a main purpose that why we need to draw this distribution function in the case with the CDF versus as a current. Okay, so we will take a break and come back at the 11:10.
修订版的。
没有啊，他们马上去。这家东西可以吗？我发上去了，我这边，
那我跟你。
没有，不能进。我可以帮你弄，但是。哦。看你。
是我直接撕掉。你觉得要撕掉怎么样？
你就撕掉就好了。我觉得你做备案就撕掉。不然你上去我也没办法进来。这样。
好了，到这里。没有，我这样。Yes.
I need your signature.
Yes.
And
Okay.
Okay. And
土豆。
Okay, so we'll continue. In addition to the cumulative distribution function, actually there's one is also very important. Later we will need to very often to mention this as well. It's what we call the probability density function. The PDF, the probability density function. So that's the typical function that defines. This is a PDF for the normal distribution function that has a similar mathematical form as shown below, which we have the fx is equal to which is 1 over this sigma 2 pi power of 1 over 2 exponential minus x minus mu square and 2 sigma square, and this is the function that can describe this normal distribution function, which we have the plot as shown here. And normally, for the normal distribution function, we have this the bell-shaped distribution. Where the center we call as a mu here, and then we have the different standard deviation, which have a mu plus a sigma and mu plus a 2 sigma, and also this one mu minus sigma and mu minus 2 sigma here. So that's a general figure for this normal distribution function, and where quantities of sigma and mu are defined in this bell shape as well. And sometimes we will express S in the standard unit, where we express by Z is equal to x minus mu over sigma, and then we can reform the equation as shown here. And there's an important concept, that's what we call the statistical process control, SPC. And then from this statistical process control, we'll come out with what we call the 6 sigma, this kind of concept. So a state-of-the-art IC fabrication process has approximately more than 50 masks. More than 50 max level and more than 600 individual process steps. So this is information from the y-axis, which is the area max versus different technology node, and you can see when the technology reach below the 11 nanometer, that's already have the average around 676 masks. And each mask and each process can introduce additional defects, and which can potentially impact the yield and reliability of an IC chip, as we mentioned in the last chapter, that once we have more process step here, and this will highly influence our yield and reliability. So then the question is how to handle the control of the process and defect introduced by process. That's one of the critical challenges. And in here, by using the concept, the knowledge that coming from the normal distribution, as we have seen, this is a typical PDF equation for normal distribution function is shown me here. And this equation is widely employed in industry to monitor the extent of process of production quality control here. So we use this kind of concept as a process control, especially the very important parameter that we call the sigma here. The sigma is a measure of the spread of the major process variables, for example, the threshold voltage here. And then, so if you try to look at this normal distribution function here, we have this center unit, center value, and we have a different sigma, and then sigma means a standard deviation. So with a positive and negative 1 sigma, with a positive and negative 1 sigma, actually the overall amount within inside this region is 68.25% here, and with a 3 sigma, with a 2 sigma upper and a lower, as shown me here. We got the 95% of this overall content with positive and negative 2 sigma here. So we can use this sigma as a measure of the spread of the one particular process variables here. For example, the threshold voltage. And therefore, normally we will consider the graph, for example, which we have as a target threshold voltage in the middle, and we can define as one particular allowed range. For example, the bell shape is like in this way, and then our allowed range is 10% variation of our threshold voltage. So if the bell shape overall, the sigma here is inside this range, we can get a very pretty good uniform of our threshold voltage. And then beyond this criteria, then we consider the yield equal to 0. So therefore, we can use this sigma as a measure of this spreading for this certain parameter. And also, from this graph, we show the threshold voltage has limits. Beyond this limit, a chip or entire wafer is considered the zero yield, as shown here. This is beyond this is we consider zero here. So there's an acceptable range for the critical parameter. Now we use the threshold voltage, but in the reality, every kind of parameter has its own range. For example, the oxide charge, oxide thickness, and so on and so on. So we consider this concept of using the sigma as a spreading measurement. Therefore, we can try to define as a two parameter here. The parameter, our targeting performance parameter should always between the upper control limit that we call the UCL, and also the lower control limit. The LCL. So where is the UCL? This is UCL, and this is LCL. So this is the device that fabricate at a different time. So you can see this is the x-axis as a time, as a date, and then we try to set out a certain upper control limit and then the lower control limit, and each fabricate device will be characterized with a certain parameter, and we hope all these parameters should be in the range of this UCL and LCL here. But the next question is, how do we define this UCL and LCL? So therefore, we introduce a concept as a 6 sigma. So if you look at the normal distribution, and then in the range between the positive and -1 sigma, that contains the overall of around 68%. But the positive 2 and -2 sigma, that contains around 95%. But in the end, if we take into account the amount of the testing data, testing device in the range between the positive and -3 sigma, that will be approximately beyond 99%, which is very close to the 100%. It's already 99.7. That will be lie between this +3 and -3. And this +3 and -3, that's why we call it as a 6 sigma. So it's very important that you will very often to hear about the 6 sigma process control. The 6 sigma means that this is the meaning coming from the normal distribution from the +3 sigma and -3 sigma. In the end, that can consider more than 99% of the overall testing data. So if now the spread from +3 to -3 as a small compared to the UCL and LCL, so then we have a high certainty that the parameter is controlled well enough for our purpose. So what does this mean? This means that this 6 sigma here, minus 3 sigma, positive 3 sigma, these are the 6 sigma range. If this 6 sigma range is lying in between the LCL and UCL, then we are consider the parameters here are well controlled. So that's the purpose. So we always hope that in the end, the 6 sigma can be lying in a certain range, and this range is a certain the value that we accept, that we define, and we think this is a good range. On the other hand, if we have the distributions, if we have this our distribution, our normal distribution, showing that the result is like this one, and our LCL is here, our UCL is here, and with this distribution, then the 6 sigma can be very wide, as shown me here. So this is our 6 sigma range. Then apparently this 6 sigma range is much larger than our control limit. So that suggests that this process is a poor control. So that's the ideas here. We use 6 sigma as one of the indication, and then we want to make sure that our control limit is always of 6 sigma will be in the range of this control limit, and then we consider that our overall process, our parameter, our target performance are well controlled. But on the other hand, if our the 6 sigma is beyond this control limit, that suggests that we have a poor control. So beyond this, there's a more sophisticated measure to measure the term between what we call as CP and then the CPK here. So CP measures the short-term capability. And then the CPK means the long-term process capability. And there's a correlation in between. The CP can be calculated as CP is equal to UCL minus LCL divided by 6 sigma. And on the other hand, the CPK is calculated by CP over 1 over the K divided by the K, and where the K is the mean, the ratio of the mean drift to this value, which is the UCL minus LCL over 2. So this is a definition of this CP and also the CPK here. And from the right top figure, we can clearly see that if the CP value is larger than 1, we have the relative narrow distribution. But also, the concept between the short term and long term can be understood from this graph. So, if you consider the short term, that means each one has its own distribution. So we have many small distribution in between. For each device here. But long term means that we look at the overall situation, which in the end, every individual distribution can be merged with one overall distribution, and that's we consider as a long term. And also, some more clarifies between when we talk about the distribution, and we also want to understand, especially the central value versus standard variation. We have the concept, what we call the accuracy versus the precision. So with respect to the measurement, the most often asked question are, how accurate are they? And then what precision are they made? So here is 4 different examples. Just try to illustrate that from this sigma, and then also the calculation between x1 and x0, and then we can understand that there will be the 4 cases. Sometimes has a good precision, but with a poor accuracy. But sometimes we have the poor precision, but with a good accuracy. So for example, in the case with A here, with this kind of the distribution, we have a smaller sigma. But also the small x1 minus x0 here. So the smaller x1, like this is kind of like when you try to shooting on target, and then you have the average of the shooting, the center point of your shooting will be x0, and then your targeting will be the x1 here. So once you have the small x1 minus x0 here, so this deviation x1 minus x0 that suggests as accuracy. So therefore, in this case, because we have a smaller sigma, small x1 minus x0, so we got this as a good precision and then a good accuracy. But on the other hand, if you look at the case B, which we have a larger sigma, but then we have also still have the small x1 minus x0. So this is because of a large sigma that suggests this is a case with a poor precision. But in the end, the center point still has a smaller range compared to the x1. So that's still the good accuracy here. And in the case with in this case C, we have the small sigma, but now we have very large x1 minus x0. So this is a case of good precision but a very poor accuracy. And also the last case is we have the large sigma but also the large x1 minus x0. And therefore in this case it's a poor precision and a poor accuracy. So this is a difference between the accuracy and then the precision. If you look at one particular distribution but want to compare with your targeting value here. And then the next is we want to talk more about how do we derive the failure rates here. So normally the reliability implies the time-dependent value. Therefore, we must have to include the time factors. So we have to include a time factor in every consideration. For example, in the case with the CDF, where we have been talking about the CDF, so we have to take into account the time. So therefore, the CDF now has to be rewritten as an integration of Fy dy, but now we have to put the time factors inside from minus infinite to the t. So that's a CDF with time consideration, where the lower time limit is taken to be the minus infinite instead of 0. That's for the mathematical purpose, and y is the dummy variable for these integrations. And for given populations, ft is a fraction that fills up to time t, and it is related to the PDF, probability density function, and therefore we can express the PDF, that's a probability density function, as ft is equal to derivative of the CDF, the dft divided by dt. So the correlation between the CDF and PDF can be shown in here. Also, we have to define as a reliability, or what we call as a survival function, RT. So this reliability function can then be defined to indicate as a survival function. So that means the RT, because this is a survival function, so what we can do is just try to remove the value probability, and now we can get the survival, right? So the equation is simple. 1 minus the CDF. So the CDF, capital FT, is a cumulative value function. So if we do the 1 minus of this cumulative value, for sure that means this is a survival function. This is a reliability function. So then the value rate also sometimes is known as a hazard rate. The lambda t is defined as a number of a product, for example device, that fell between t and t plus delta t per time increment delta t as a fraction of those that survive to time t. Okay, so that's the text is very complicated, but if you try to write it as an equation, is much getting clearly. So our lambda t is equal to the ft plus delta t minus ft in the small incremental of the minus the ft. So we consider in this a range in the time between the t plus t divided by this t, and also as a fraction of those survive. As a fraction of those that survive to time t, which means we have also divided by 1 minus ft here, because of this is this one. So that's a failure rate. So you have the number of products fail between specific time domain over the survive of your device. So that's a 1 minus ft. Although this equation is a little bit complicated, but as usual, this can be highly simplified, because here, because this one this one is exactly just equal to this one, right? This function is equal to this function. So therefore, this will become the small ft divided by 1 minus ft. And we already mentioned that we call this as a reliability function or survival function. In the end, this equation is become very simple, just like this one. We have a small ft, which is a PDF function divided by survival function. That's all. So that's how we get this value rate. Because right now we incorporate the time factors here, and later we will do the one by one to see that if we really put the exponential distribution function, what will be the value rate? If we put the Weibull distribution function here, what will be the value rate? So that's the purpose why we explain this at this moment, because later we will put a different distribution function, because you know the CDF is a distribution function. So if you consider all kinds of various distribution functions, what would be the value rates? So now let's start to look at the one by one. The first one is the most well known. It's an exponential distribution function. So this one, we consider the PDF, which is a probability density function for this exponential distribution function, which is equal to ft is equal to lambda of 0 exponential minus lambda zt, right? So that's a typical exponential decrease distribution function. But now the time is not incorporated in this function yet, so we are actually interested in the time factor from the this equation. So therefore we start to do the integration of the time, where we can have this cumulative distribution function, where we have the integration from minus infinite to the t, and the same, we just put the lambda 0 exponential minus lambda 0 r dr. And this calculation is very simple. That's equal to 1 minus exponential minus lambda 0 t. So that's a CDF, very simple. And then with what we learned from last slide, the value rate, so we can have the value rate calculation here, which is equal to ft, right? So we have ft on top divided by 1 minus capital FT here. And therefore, we can put everything we know here. This is lambda 0 exponential minus lambda 0 t over 1 minus exponential minus lambda 0 t. And in the end, although the equation looks complicated, But if you take your time to think about this, the conclusion is very simple. We got the lambda 0 here. And then most importantly, the lambda 0 is a constant. So we should consider the exponential distribution function. In the end, we found out that actually a failure rate is a constant. This is why in most of the time, when we do the certain consideration, we always use the exponential in the beginning, because the constant is always the most straightforward consideration in the first sense. If we try to calculate the loss of failure rate, we always hope that if that can be the constant failure rate, then the calculation can be way so simple, or extrapolation can be very straightforward. So now you can see that the reason why the exponential distribution function is very often used as a first attempt, because of the underlying failure rates inside this distribution function is a constant, which is a very I would say very simple. That's why in the end cause this exponential distribution function is very popular. So therefore, we can start to draw the one by one from the PDF, CDF, and also the hazard function, which is the failure function. So in the beginning, we always starting from our PDF equation. So the PDF where we shown before, the PDF, sorry. For this exponential distribution, which is Ft is equal to lambda 0 exponential minus lambda 0t. And therefore, if we try to plot this for the PDF, if we consider the x-axis as a 1 over lambda 0, 2 over 3 over lambda 0 here, then we can get this exponential distribution, right? So that's a very straightforward plotting here, because this is a normal, very normal exponential decreasing function. And then if we try to plot the CDF, so again, if you back to look at the CDF function, the CDF is the capital Ft is in the end equal to 1 minus exponential minus lambda 0t. So actually just 1 minus of this equation. 1 minus equation. So then we can expect the CDF here should be approximately like in this way. Right? And then also this is with respect to the 1 over lambda 0, 2 over 3 over lambda 0 here. And then the last one, what we're actually interested in is failure rate. And we already mentioned that sometimes we call this as a hazard rate here. And therefore, the function that including the hazard rate, that we call as a hazard functions. And from previous last slide, we have already derived that with a case with exponential distribution and our failure rate is constant, which is lambda 0 here. And therefore, this will become as a lambda 0 with respect to the 1 over lambda 0, 2 over lambda 0, and 3 over lambda 0 here. So now I hope you can start to a little bit able to accept this kind of equation, because of course if you don't see the plotting, probably you will feel like this equation looks very complicated. But with step by step, I think now with this plotting, you can figure out that this calculation is pretty easily understand and quite makes sense, and then the results are very easily understood. So due to ease in dealing with a constant failure rate, the exponential distribution function has proven popular as a traditional basis of a reliability modeling. So that's why I have already mentioned that we always try to consider exponential distribution function as a modeling first, because the failure rate is constant, and then we all have the feeling that if everything can be modeled with a constant, that would be the perfect. So we always try the constant failure rate as a beginning. And let's look at the how we actually use this constant failure rate for the modeling and then for lifetime prediction. This is coming from, although it's a very early time, but you can see that back to that moment, how this the company, the institute, to do the lifetime modeling for their component, for their product. And this is the reference that coming from the military handbook. So the military handbook, that means this is a handbook for all of the military weapons, and then the component for the military weapons. How do they estimate the failure rate and lifetime? This is coming from the USA Army for the military handbook. They look at the transistor. This is a transistor under the low frequency. So they make this handbook as a reference that later when any of the user want to understand the failure rate, they can always refer to this information. And this is under the consideration of the N-channel and P-channel silicon FET. So there's one specific consideration. And because at that moment, of course, this is very old technology. So, and also back to that time, probably our understanding for reliability is not needed as we have for today. At that moment, probably lots of things can be easily understood with constant value. So he just provides the equation for the lambda p as shown in here, and this just overall of the lambda p is the part failure rate. So every component, the overall component failure rate, just a product of each constant value as shown in here. So this is lambda p is a part failure rate, and lambda b is a basic failure rate, usually expressed as a model related to influence of electrical and temperature stress on the part here. So individual p factor takes into account the raw temperature, quality, and environment as well. So how do we use this the handbook to do failure rate estimation, just look at the example here. If we consider as a plastic cap small signal switching MOSFET. So the first condition is that which is a MOSFET. So let's just look at the MOSFET here. This is MOSFET, and then lambda B, which is 0.012 as a base failure rate. And this MOSFET is going to be operate at the 30 Celsius degree. So let's just look at the 30 Celsius degree, which is here. This is the impact of the temperature on the failure rate in a space flight. And also, this in the end we can start to estimate all of the part failure rate. We consider all of each part. This is the best failure rate for the MOSFET. This is for the 1.1. This is means that this device, when device operate at a 30 Celsius degree, and then the 8, which is probably here, probably is like in from the here. And also we have the 0.5, which is coming of 8 is coming from the plastic, because they mentioned this is using in the plastic. And then we all consider the each small contribution coming from this table that look out for the each specific consideration. We can have this, the part failure rate, which in the end will be equal to this one. (0.037 per 10 to 6 hour), or we just call it because sometimes it's just a way difficult that we always have to call as a per 10 to 6 hour, and therefore we just define as what we call the FIT, fits here. So the fits, which is abbreviation coming from the failure in time. So it's a number of the failures that can be expected into the 1 billion, that's a 10 to 9 device hour of operation. So that's the definition of the fit is a number of failure that can be operated in the 10 to 9 device hour operation. So this is one example that how we actually use the failure rate estimation that for the one component, and then we take into account for the each factor coming from the MOSFET, coming from the temperature, coming from the plastic, and so on and so on. And then in the end, the overall failure just a combination, just a product of the each one combination. And this is coming from the military handbook. Although probably if you look at from the today, this might not be so accurate, because nowadays our semiconductor device is very complicated, but you can still see that this method has been certain verified with a certain time being in the past, that in the military they even adapt this method to do the failure rate modeling, and especially in the end they want to understand what is the lifetime of their device. Okay, so we will probably stop here because the rest of the tool will be a little bit complicated, because it's something that normally you should never heard before. So we'll spend some more time in next week to discuss the rest. Okay.